This is audio recording for visually impaired students. So let's start electrochemistry. Part 1, Electrolytic conduction and transport number. Electrolytic and metallic conduction and factors affecting them. So what are electrolytic metallic conductions? Substances which allow electricity to pass through them are known as conductors, whereas substances which do not allow electricity to pass through are known as insulators. Conductors are divided into two classes. Number 1, those which conduct electricity without undergoing any decomposition. These are called electronic conductors. Example, metals, graphite and certain minerals. As the name indicates, the conduction in this case is due to flow of electrons. Those which undergoes decomposition when current is passed through their aqueous solution or melt. These are known as electrolytic conductors or electrolytes. Example, solution of acids, bases and salts in water, fuel source, etc. In this case, the flow of electricity is due to the movement of ions. Electrolytes are further classified into two main categories as strong electrolytes and weak electrolytes. Strong electrolytes are substances like strong acids, example HCl, HNO3, H2SO4, etc. Strong bases, example NaOH and KOH, etc. And most of the inorganic salts. These dissociates almost completely in the aqueous solution or in the molten state and hence conduct electricity to a large extent. Weak electrolytes are substances like weak acids, example CS3COOH, HCN, H2CO3, S3PO4, etc. and weak bases, example NH4OH, CaOH twice, AlOH thrice, etc. These have low degree of dissociation and hence conduct electricity to a small extent. Substances like sugar, urea, etc., the solution of which do not conduct electricity are known as non-electrolytes. Factor affecting electrolytic conduction. The conductance of the solution of an electrolyte depends upon the following factors. Intraionic attractions, which depend upon the interactions between the ions of the solute and hence are called solute-solute interactions. On the basis, the substances are classified as strong electrolytes and weak electrolytes as already mentioned. Number 2, solvation of ions, which depends upon the interaction between the ions of the solute and the molecules of the solvent and hence are called solute-solvent interactions. Strong electrolytes are almost 100% ionized in the aqueous solution, whereas weak electrolytes are less than 10% ionized in the aqueous solution. However, there are many electrolytes whose behavior is intermediate between strong and weak electrolytes, that is, their dissociation is less than 100% but greater than 10%, and similarly, their conductance is less than that of strong electrolytes but greater than that of weak electrolytes. Such electrolytes are called moderate or intermediate electrolytes. Example, orthochlorobenzoic acid, orthonitrobenzoic acid, and cyanoacetic acid. Number 3, viscosity of solvents depends upon the solvent-solvent interactions. The effect of all these factors decrease with increase of temperature. Hence, the electrolytic conduction increase with increase of temperature. On the other hand, the electrical conduction of the electronic conductors decrease with increase of temperature. Alternatively, the factors on which the electrolytic conduction depends are as follows. Number 1, nature of the electrolytes. Strong electrolytes ionize almost completely in the solution and hence conduct electricity to a large extent, whereas weak electrolytes ionize to a small extent and hence conduct electricity also to a small extent. Number 2, nature of solvent. Electrolytes ionize more in a pore solvent, hence greater is the polarity of the solvent, greater is the ionization, and hence greater is the conduction. Number 3, concentration of the solution. Higher the concentration of the solution, less is the conduction. This is because in a weak electrolyte, the ionization is less, whereas in a strong electrolyte, the intraionic attractions are high at higher concentration. With dilution, intraionic attractions decrease and hence conduction increases. Number 4, temperature. On increasing the temperature, the dissociation increases and hence the conduction increases. Difference between metallic conductors and electrolytic conductors. The main points of difference between metallic conductors and electrolytic conductors may be summed up in table 2.1. Metallic conductors. Flow of electricity take place without the decomposition of substances. Electrolytic conductors. Flow of electricity takes place accompanied by the decomposition of the substances. Number 2. Flow of electricity is due to the flow of electrons only, that is, there is no flow of matter. The conductance depends upon the structure and density of the matter and the number of valence electrons per atom in metallic conductors. In electrolytic conductors, flow of electricity is due to the movement of ions, hence there is flow of matter. In metallic conductors, the electrical conduction decreases with increase of temperature. This is because kernels start vibrating, which produce hindrance in the flow of electrons. In electrolytic conductors, the electrical conduction increases with increase of temperature. This is generally due to increase in dissociation or decrease in the interionic attractions. In metallic conductors, the resistance offered by metals is also due to vibrating kernels. In electrolytic conductors, the resistance shown by an electrolyte solution is due to factors like interionic attractions, viscosity of solvent, etc. Electrical resistance and conductance. Every substance offers resistance to the flow of electricity to a small or large extent. The law that gives the exact value of the resistance is known as Ohm's law. It states that if to the ends of a conductor a voltage E is applied and a current I flows through it, the resistance R of the conductor is E by I. Current is generally measured in amperes, whereas voltage is measured in volts. If 1 ampere current flows through a conductor when a voltage of 1 volt is applied to it, the resistance of the conductor is taken as 1 ohm, written as 1 ohm. Thus, according to Ohm's law, R is equals to E by E, or ohms is equals to volts upon ampere. In terms of SI base units, ohm is equals to kg meter square upon S cube A cube. This is explained below. Ohm is equals to V by A is equals to work per unit charge upon A is equals to work by charge into I by A is equals to F into L into I upon A into S into A. So M into A into L upon A square S is equals to kg into m S की power minus 2 into m upon A की power 2 S is equals to kg m square upon S cube A square. It is seen that like metallic conductors, solution of all electrolytes also obey Ohm's law. It is obvious that a substance which offers greater resistance will allow less electricity to flow through it. This result also follows from Ohm's law, according to which I is equals to I1 by R. The reciprocal of the electrical resistance is called the conductance. It is usually represented by C. Thus, C is equals to 1 upon R. It is a common practice to speak of the conductance of a solution rather than its resistance. Units. The units of conductance are Siemens or reciprocal ohms, written as ohm inverse or MHO or Simon. 1S is equals to 1 ohm inverse. For example, if a solution has a resistance of 10 ohms, it is said to have a conductance of 1 by 10 ohm inverse or 1 by 10 MHOs or 1 by 10 ohm inverse or 1 by 10 Siemens. Specific equivalent and molar conductivities, conductances and relation among them. Specific conductance or specific conductivity, or simply called conductivity. It is observed that resistance R of a conductor is number 1 directly proportional to its length of the conductor. Number 2 inversely proportional to its area of cross section, that is R is proportional to L by A, or R is equals to rho L by A. Where rho is a constant of proportionality is called specific resistance or resistivity. Its value depends upon the material of the conductor. The reciprocal of resistivity is known as specific conductivity or simple conductivity. It is denoted by kappa. Thus, if K is the specific conductivity or C is the conductance of the solution, then R is equals to 1 by C and rho is equals to 1 by K. 1 by C is equals to 1 by K into L by A. K is equals to C into L by A. Now, if L is equals to 1 centimeter and A is equals to 1 square centimeter, then K is equals to C. Then, specific conductance or specific conductivity, or simply called conductivity of a solution, is defined as the conductance of a solution of 1 centimeter length having 1 square centimeter as the area of cross section. Alternatively, it may be defined as conductance of 1 centimeter cube of the solution of the electrolyte, or in terms of SI based unit, it is defined as the conductance of 1 meter cubic of the conductor. If the volume of the solution is V centimeter cubic, the specific conductance of such a solution at this dilution V is written as Kv. Similarly, at concentration C, it is represented as Kc. Units resistivity rho is equals to or A by L is equals to ohm centimeter square upon centimeter is equals to ohm centimeter. Specific conductance K is equals to 1 by rho 1 upon ohm centimeter is equals to ohm inverse centimeter inverse. Equivalent conductance or equivalent conductivity. For comparing the conductance of the solution of different electrolytes, it is essential that number 1, the volumes of the solution should be same. Number 2, they must contain such definite amounts of the electrolytes which give ions carrying the same total charge. The best choice is therefore to consider the solutions having equal volumes and containing their corresponding gram equivalent masses. The conductance of such a solution is called its equivalent conductance. Hence, equivalent conductance of a solution at a dilution V is defined as the conductance of all the ions produced from 1 gram equivalent of the electrolyte dissolved in V centimeter cubic of the solution when the distance between the electrode is 1 centimeter and the area of electrode is so large that the whole of the solution is contained between them. It is represented by lambda equivalent. Relationship between equivalent conductance and specific conductance. The equivalent conductance of a solution is usually not found directly but is calculated from the specific conductance. The relationship between equivalent conductance and specific conductance may be obtained as follows. Consider a rectangular vessel with its two opposite walls 1 centimeter apart and made of some metal sheet so that these act as the electrodes. Case 1. Suppose 1 centimeter cubic of the solution containing 1 gram equivalent of the electrolyte is taken in the vessel. The conductance of this solution will be then its specific conductance. Further, if 1 centimeter cubic of the solution taken contains 1 gram equivalent of the electrolyte, the conductance of the solution will be its equivalent conductance by definition. Thus, when 1 centimeter cubic of the solution containing 1 gram equivalent of the electrolyte is considered, the equivalent conductance is equal to its specific conductance. Case 2. Suppose 4 centimeter cubic of the solution containing 1 gram equivalent of the electrolyte is taken. The conductance of the solution will be still equal to equivalent conductance at this dilution, but now there will be 4 cubes each of volume 1 centimeter cubic as shown in figure 2.2. The conductance of each 1 centimeter cubic of the solution is equal to its specific conductance, so that the total conductance of the solution, that is equivalent conductance, is 4 times the specific conductance. In general, if the volume of the solution containing 1 gram equivalent of the electrolyte is V centimeter cubic, we have equivalent conductance is equals to specific conductance into V. In terms of concentration, if the solution has a concentration of C gram equivalent per liter, that is C gram equivalents are present in 1000 centimeter cubic of the solution, then the volume of the solution containing 1 gram equivalent will be 1000 by C. Hence, the above expression may be written as lambda equivalent is equals to Kc into 1000 upon C equivalent is equals to Kc into 1000 upon normality. Note carefully that in above expression V is the volume of the solution in centimeter cubic containing 1 gram equivalent of the electrolyte and C is the concentration in gram equivalent. Units: lambda equivalent is equals to K into V is equals to ohm second inverse centimeter inverse into centimeter cubic upon gram equivalent. So it will be Simon meter square per equivalent in SI units. Molar conductance or molar conductivity. The molar conductance of a solution is defined in a manner similar to that of the equivalent conductance as under. The molar conductance of a solution at a dilution V is the conductance of all the ions produced from 1 mole of the electrolyte dissolved in V centimeter cubic of the solution when the electrodes are 1 centimeter apart and the area of the electrode is so large that the whole of the solution is contained between them. It is usually represented by delta M. Relationship between molar conductance and specific conductance. As in the case of equivalent conductance, the molar conductance is related to the specific conductance as follows. Lambda m is equals to Kv into V. Lambda m is equals to Kc into 1000 by C is equals to Kc into 1000 by molarity, where K is the specific conductance and V is the volume of the solution containing 1 mole of the electrolyte, and C is the molar concentration, that is mole per liter. Variation of conductance, specific conductance, equivalent conductance, and molar conductance with dilution. In general, electrolytic conductance as well as the equivalent conductance and molar conductance increase with dilution, whereas the specific conductance of an electrolytic solution decrease with dilution. The reason for such a behavior are explained below. The conductance of a solution is due to the presence of ions in the solution. The greater the number of ions, the greater is the conductance. As on dilution, more ions are produced in solution, so the conductance should also increase on dilution. The specific conductance of an electrolyte falls with dilution because the total number of current carrying particles, that is ions, increases with dilution, but ions present per centimeter cube of the solution become less and less on dilution. However, the increase of equivalent and molar conductance on dilution is due to the fact that these are products of specific conductance and the volume V of the solution containing 1 gram equivalent or 1 mole of the electrolyte. As the decreasing value of specific conductance is more than compensated by the increasing value of V, so the values of lambda equivalent and lambda m increase with dilution. Variation of molar conductance with concentration for strong acid and weak electrolytes. As already mentioned in the beginning of this chapter, there are two types of electrolytes, namely strong electrolytes and weak electrolytes. The variation of molar conductance with concentration or dilution for each of these electrolytes is briefly discussed below. Conductance behavior of strong electrolytes. As discussed later in more details in section 2.7, the molar conductance of strong electrolytes is found to vary with concentration according to the equation delta M is equals to delta dot M minus B under the root C, where B is a constant depending upon the type of electrolyte, the nature of solvent, and the temperature, and delta dot M is the molar conductance at infinite dilution called limiting molar conductance. This equation is called Debye-Huckel or Sagar equation and is found to hold good at low concentration. Thus, if delta M is plotted against under the root C, a linear graph is obtained for low concentration, but it is not linear for higher concentration as shown in figure 2.5, in which KCl has been taken as an example of strong electrolyte. Further, the curve obtained for a strong electrolyte shows that there is small increase in conductance with dilution. This is because a strong electrolyte is completely dissociated in solution, and so the number of ions remains constant. At higher concentration, the greater interionic attractions retard the motion of remains ions, and therefore the conductance falls with increasing concentrations. With decrease in concentration, that is with dilution, the ions are far apart and therefore the interionic attraction decrease, due to which the conductance increases with dilution and approaches a maximum limiting value at infinite dilution, designated as delta M, delta dot M, or delta infinity M. Conductance behavior of weak electrolytes. As a weak electrolyte dissociates to a much lesser extent as compared to a strong electrolyte, therefore the conductance of a weak electrolyte is much lower than that of a strong electrolyte at the same concentration. This is shown in figure 2.5, in which acetic acid has been taken as an example of a weak electrolyte. Further, the curve obtained for a weak electrolyte shows that there is a very large increase in conductance with dilution, especially near infinite dilution. This is because as the concentration of the weak electrolyte is reduced, more of it ionizes. Thus, increase in conductance with decrease in concentration is due to the increase in the number of ions in the solution. However, it does not reach a limiting value. The experimental results of molar conductance of KCl and CS3COOH different concentration given below further help to understand the variation more clearly. Further, from the plot shown in figure 2.5, it is observed that the plot for a strong electrolyte becomes linear near high dilution and thus can be extrapolated to a zero concentration to get the value of molar conductance at infinite dilution, that is delta dot M. However, for a weak electrolyte, such an extrapolation is not possible, as it clear from the plot for acetic acid in figure 2.5. Experimentally also, it is not possible to determine the delta dot M value for a weak electrolyte, as it does not approach a limiting value. The problem was finally solved by Kulrosh, who put forward a law known as Kulrosh law, as discussed in section 2.8. Arrhenius theory of ionization. Postulates of Arrhenius theory. To explain a number of phenomena related to electrolytes such as conductance, electrolysis, anomalous behavior of electrolytes toward colligative properties, that is higher values of osmotic pressure, elevation in boiling point, depression in freezing point, and lowering of vapor pressure than expected. Arrhenius in 1887 put forward a theory about the electrolytes. This theory is known as Arrhenius theory of electrolytic dissociation. The main points of this theory in a modified form are summarized below. An electrolyte, when dissolved in water, splits or dissociates into positive and negative charged particles called ions. The process is called ionization, or more correctly, electrolytic dissociation. Example: NaCl gives Na positive plus Cl negative. MgCl2 gives Mg2 positive plus 2Cl negative. Al2SO4 thrice gives 2Al3 positive plus 3SO4 2 negative. The total charge carried by the positive ions is equal to that carried by the negative ions, so that the solution as a whole is electrically neutral. On electrolysis, the positive ions migrate towards cathode and hence are called cations, while the negative ions migrate towards anode and are therefore called anions. Number 4. The ions formed constantly reunite to form the undissociated molecule till ultimately there is an equilibrium between the ions and the undissociated molecule. Example: NaCl, Na plus Cl negative, MgCl2, Mg2 positive plus 2Cl negative, Al2SO4 thrice, 2Al3 positive and 3SO4 2 negative. In other words, the whole of the electrolyte may not dissociate into ions, instead only a part of the electrolyte may dissociate into ions. The fraction of the total number of molecules of the electrolyte that dissociate into ions is called the degree of ionization or dissociation. It is denoted by alpha, that is degree of association. Alpha is equals to number of molecules dissociated upon total number of molecules taken. Number 5. The degree of dissociation increases with dilution and becomes maximum at the infinite dilution. Number 6. The conductance of an electrolytic solution is due to the ions produced by the dissociation of the electrolyte. Greater the dissociation, higher is the conductance. Substances like mineral acids, alkalis, and most of the salts which show a high conductance is due to the fact that they possess high degree of dissociation, that is, their molecules are almost completely dissociated into ions in aqueous solution. Such substances are called strong electrolytes. On the other hand, substances like organic acid and bases and some of the inorganic acids like H2CO3, S3PO4, etc., and inorganic bases like NH4OH, CaOH twice, etc., which show poor conductance, is due to the fact that they possess low degree of dissociation, that is, they are only partially dissociated in the aqueous solution. Such substances are called weak electrolytes. 7. The ions produced by the dissociation of an electrolyte behave like molecules towards colligative properties. For example, each NaCl molecule dissociates to give two ions with Na positive and Cl negative. Hence, the observed value of any colligative property is double than the expected value. Number 8. The properties of an electrolyte are the properties of its ions. For example, the properties of an acid are due to the H positive ions furnished by it in the aqueous solution. Similarly, the properties of a base are due to the OH negative ions produced in the aqueous solution. Evidence in favor of Arrhenius theory. The direct evidence for the Arrhenius theory came from the X-ray studies, which showed that solid substances which behaved as strong electrolytes existed in the form ionic and not in the molecular form. Example, NaCl is found to exist as Na positive Cl negative. Further, Arrhenius theory is able to explain a number of facts and phenomena related to electrolytes which lend support to the theory. A few of these phenomena are briefly explained below. Number 1. Electrolytic conductance. It has been explained in postulate 6 of the Arrhenius theory that the conductance of the solution of an electrolyte is due to the presence of the ions produced by the electrolyte on dissociation. Strong electrolyte possesses high degree of dissociation and hence show greater conductance, whereas weak electrolyte dissociate to a small extent and hence show low conductance. Number 2. Variation of conductance with dilution. It is observed that the specific conductance decrease whereas conductance as well as equivalent conductance increase with dilution. The explanation is evidently based on postulates 5 and 6 of the Arrhenius theory. The equivalent conductance and dissociation of the electrolyte vary in such a similar manner with dilution that the degree of dissociation of an electrolyte at any concentration can be explained in terms of equivalent conductance as follows. Alpha is equals to lambda C upon lambda naught. Lambda C is the equivalent conductance at the given concentration and lambda naught is the equivalent conduction at infinite dilution. Number 3. Electrolysis. According to postulate 1 of the Arrhenius theory, an electrolyte when dissolved in water dissociate into ions. Thus the formation of the electricity is only to direct the ions toward the electrodes. Colligative properties. The reason for the anomalous results observed about the colligative properties for the solution of the electrolyte has already been given in postulate 6 of the Arrhenius theory. The quantitative explanation of the anomalous results about colligative properties of strong electrolytes was given by von Hoff. He introduced a factor I called von Hoff factor defined by the expression I is equals to observed value of colligative property upon normal value of colligative property. The factor I could be determined experimentally by dividing the observed value of a colligative property, that is osmotic pressure, lowering of vapor pressure, elevation in boiling point or depression in freezing point, with that of solution of a normal substance like sucrose having the same molar concentration. The want of factor I could be used to find the degree of dissociation as follows. Number 1. For electrolytes of the type AB, example NaCl, KCl, etc. Suppose we start with 1 mole of the electrolyte and alpha is the degree of dissociation. Then we have AB in equilibrium, A positive plus B negative. Number of moles before dissociation 1, 0, 0. Number of moles after dissociation 1 minus alpha, alpha, alpha. Total number of moles after dissociation is equals to 1 plus alpha. Assuming normal behavior, that is, if there were no dissociation, number of moles would have been is equals to 1. Since the value of a colligative property is proportional to the number of particles, which in turn is directly proportional to the number of moles, want of factor I would be given by I is equals to 1 plus alpha by 1, so that alpha is equals to I minus 1. Number 2. For electrolytes of the type AB2, example BaCl2, MgCl2, etc., starting with 1 mole of the electrolyte and assuming that alpha is the degree of dissociation, we have as before AB2 in equilibrium with A2 positive plus 2B negative. Initial number of moles 100. Number of moles after dissociation 1 minus alpha, alpha 2 alpha. Total number of moles after dissociation is equals to 1 plus 2 alpha. Hence, as in the earlier case, I is equals to 1 plus 2 alpha by 1, or 2 alpha is equals to I minus 1, or alpha is equals to I minus 1 by 2. The values of alpha found from these measurements and those found from the expression alpha is equals to delta C by delta naught were found to be in fair agreement with each other for a number of electrolytes. This lent a great support to the Arrhenius theory. In general, for an electrolyte of the type AXBY, we have AXBY in equilibrium, XAY positive plus YBX negative. Number of moles before dissociation 100. Number of moles after dissociation 1 minus alpha, X alpha, Y alpha. Total number of moles after dissociation is equals to 1 plus alpha into n minus 1. where n is equals to x plus y represents the total number of ions produced from the dissociation of one molecule of AXBY. Thus, as before, I is equals to 1 plus alpha n minus 1 upon 1, which gives alpha I is equals to I minus 1 upon n minus 1. Number 5. Ionic nature of reactions. As stated in postulate 7 of the Arrhenius theory, the properties of an electrolyte are the properties of its ions. Thus, the reaction between NaCl solution and AgNO3 solution forming a precipitate of AgCl may be explained as follows. NaCl in aqueous solution ionizes as NaCl gives Na positive plus Cl negative. AgNO3 also ionizes in the aqueous solution as AgNO3 gives Ag positive plus NO3 negative. When the above two solutions are mixed, we have Na positive plus Cl negative plus Ag positive plus NO3 negative gives AgCl plus Na positive plus NO3 negative. The reaction between any two ionic compounds in aqueous solution which takes place in similar manner. Number 6. Heat of neutralization. The heat of neutralization is defined as the amount of heat evolved when 1 gram equivalent of the acid is neutralized by the base or 1 gram equivalent of the base is neutralized by the acid. The heat of neutralization of a strong acid with a strong base is always the same, with 13.7 kilocalorie or 57.3 kilojoule. This is explained by Arrhenius theory as follows. Suppose the strong acid is HCl and the strong base is NaOH, as both are completely dissociated in the aqueous solution. The reaction between them may be written as Na positive plus OH negative plus H positive plus Cl negative gives Na positive plus Cl negative plus H2, because the salt formed with NaCl is also completely dissociated. Cancelling out the common ions on both sides, the above reaction reduces to H positive plus OH negative gives H2. Thus, neutralization may be defined simply as the process in which H positive ions given by acid combine with the OH negative ions given by the base to form unionized water molecules. As 1 gram equivalent of any strong acid in aqueous solution gives the same number of H positive ions and 1 gram equivalent of any strong base gives the same number of OH negative ions, the neutralization involves the combination between the same number of H positive ions and OH negative ions. Hence, the heat of neutralization of a strong acid with a strong base is always the same. If either the acid or the base or both are weak, the heat of neutralization is less than 13.7 kilocalorie or 57.3 kilojoule. The reason for the lower value is that a weak acid or a weak base dissociates to a small extent and some heat is used up to bring about its dissociation. For example, if the weak acid is acetic acid and the base is NaOH, they dissociate in the aqueous solution as follows. CS3COOH is in equilibrium with CS3COO negative plus H positive. NaOH gives Na positive plus OH negative. As H positive ions are removed by combining with OH negative ions, the equilibrium shifts towards right, that is, more of acetic acid dissociates. For acetic acid, the heat of dissociation is 0.5 kilocalorie per mole or 2.1 kilojoule per mole. Hence, the net heat evolved is 13.7 minus 0.5 is equals to 13.2 kilocalorie or 55.2 kilojoule. Similarly, the heat of dissociation of NH4OH is 1.4 kilocalorie per mole or 5.8 kilojoule per mole. So that heat of neutralization of NH4OH with HCl is 13.7 minus 1.4 is equals to 12.3 kilocalorie or 51.5 kilojoule. Number 7. Salt hydrolysis. It is defined as the process in which the salt reacts with water to give back the acid and base. Salt plus water gives acid plus base. Depending upon the relative strengths of the acids and base produced, the resulting solution is acidic, basic or neutral. These observations are also explained on the basis of Arrhenius theory. Ostwald's dilution law. According to Arrhenius theory of ionization, when an electrolyte is dissolved in water, there is an equilibrium between the ions and the undissociated molecules. For example, for a binary electrolyte AB, we have AB is in equilibrium with A positive plus B negative. Ostwald in 1888 pointed out that the law of chemical equilibrium can be applied to this ionic equilibrium. As a result, he obtained important relationship